Here I've pulled out some material from the sections on how to read a standard normal table, and I want to treat that sort of as a topic on its own because it's a tool that we use to answer questions that we're interested in knowing the answers to. So it's really important to be able to use that tool easily and without struggling so that when you get to the problems where you need it, you'll have it. So I want to extract the part of the material related to learning how to read that table and do it here sort of as a separate standalone topic. And I want to do that by just sort of explaining a little bit about where we stand and what the importance of this is. In situations involving some statistical problems, tables are quite often used to determine areas under sections of a curve, and these table values actually represent probabilities. So the ultimate reason we're looking for these areas that are tabled is because they're probabilities that we're interested in. In the following section, 13.4, we will lean heavily on what's called a standard normal table. And I could wait and talk about that as a part of the topic in 13.4, but because it'll help me balance the lecture times, I'm actually going to take this material out and just talk about it as a standalone topic. And then when we get back to section 13.4, I'll fill in more details about how this standard normal table helps us to solve the problems in that section. But for now, we're more learning how to do something and let the why come later. Below, I just want to say a couple of things, 2 or 3 things about the relationship between z-scores and the standard normal table for now. Let the rest of it come later. First of all, just remind you, we learned how to convert data values to z-scores. We've already done that. This so-called normal distribution of z-scores is what we call the standard normal distribution, and that standard normal distribution has a mean of 0 and a standard deviation of 1, always. But probably the most important point, one of the most important points here, is that the total area under the standard normal curve is always equal to 1. If you look at this curve, the total area underneath it is 1, and you'll also notice that it's symmetric. If you took a knife and just cut that curve right down the vertical line at 0, you would have 2 symmetrical pieces. That has an implication about area. If you cut that curve so that you only have half of it, if the total area under the curve is 1 and those 2 pieces are symmetric, that means each piece has an area of a half. So the right part has an area of 0.5 or half. The left part has an area of 0.5, and of course 0.5 plus 0.5 is 1. The total area under the curve is 1. So the idea of the symmetry of the curve and the idea that the total area under the curve is 1, and that you can cut that curve essentially into 2 symmetrical pieces whose area each has 1/2 is important. Now let's take that and use it to work problems where we have to know how to read this standard normal table. For example, this is what you will see if you have look in the appendix of the book, or if you look online in your software and pull it up. This is the standard normal table you'll get. You've got to keep in mind that this table gives you certain values that have a graphical meaning, and I put that up on the left of the table. Those areas, which is what that table shows, represent the area under the standard normal curve from 0 to the right to some particular value of z. So for any particular value of z, you can look up in that table what the area would be. So as a simple example, what if I told you to find the area under the standard normal curve from z equals 0 to 1.44? Well, that graph on the left looks of the same form as the one on the right, which means you can read that value right out of the table. All you have to do is let z be 1.44, go to the table and find it. I'll blow it up so you can see it better, and you can see that the area corresponding to a z value of 1.44 is 0.425. So you take that number, and that represents the area under the standard normal curve from 0 to 1.44. Simple. Very simple when the left boundary of the area starts at 0 and the z-value is to the right. In other words, positive. That's the simplest possible case. But we can also deal with it if z is negative by using the symmetry of the graph. If I start at 0, but I want to know the area from minus 0.144 to 0, so that the 0 boundary now is on the right, the symmetry of the graph tells me that it's the same as the area going from 0 to 1.44. That means I can still look up the 1.44 in the table and still apply it, even though it's going in the negative direction. The area of both of those pieces is the same because of the symmetry of the graph. To sort of summarize that situation, anytime you're looking for an area under the standard normal curve where one of the boundaries is 0, all you have to do is look at the z-value without paying any attention to the sign, whether it's positive or negative. Look that value up in the table, and that will be the area you're looking for. Simplest possible case. What if that's not the case? What if you're looking for something? Those are called the tails of a distribution. When you go to the far right or to the far left, those are called the tails of the distribution. What if you want to find the area of one of those tails? For instance, what about the one to the right? You want to find the area under the standard normal curve for z greater than 1.44. If you understand what the values in that table give you, this is pretty simple. And also the symmetry stuff. The fact that if you cut the curve in half at z equals 0, you get half the area to the right. So if you think about those two things together, the number 1.44 is still important. That gives you 0.425, but remember what that gives you. That gives you the area between 0 and the z value 1.44. So it gives you that. But you're not looking for that. You're looking for the shaded area to the right. Here's where the symmetry comes in. We learned that the graph is symmetric, so half the area is to the right of 0. So all you need to do is take that 0.425, subtract it from 1/2, and whatever's left is the area to the right. Easy enough. The area is 1/2 from 0 all the way to the right. You accounted for 0.425 of it between 0 and z, so the rest of it, which you get by subtraction, is the area that you're looking for. The other variation of that is if you were looking for the left tail instead of the right tail. It would be the same, right? Because of symmetry. So again, the fact that z is equal to negative 1.44 going to the left doesn't change the fact that the area is still 0.075. So again, for the tails, you can ignore the sign, plus or minus, just look up the 1.44, doesn't matter, and subtract it from 0.5, and that'll give you the area to the right of 1.44 or the area to the left of negative 1.44. The sign actually doesn't matter because the table only gives you positive z values, and because of the symmetry, you can figure it out either way. Do another one. What if I wanted to know this area? I wanted to know the area between z equal negative 1.25 and z equal 1. Now this time, the area includes, it crosses over z equals 0. Whenever that happens, what you need to do is break it into two areas and treat it as if it were two different area calculations and then add the results at the end. So you just look them up. Think of one area as being the part to the right of 0 and think of the other area as being the part to the left of 0 and work them as two separate area problems and then sum the results. So let's just start with the one on the right first. That's a standard problem where you just need to look the z value up in the table. So you go to the table, look for z equal 1, and you find out it's 0.341. That's the area to the right of 0. Now take the area on the other side. It's negative 1.25, but remember, because of the symmetry, the area is the same as it would be if you went to the right to positive 1.25. So you still just need to look up 1.25 in the table. And that comes out to be 0.394. So you have both of those areas. If you want the total area, you just add them up. 0.394 plus 0.341 is 0.735. So the area under the standard normal curve between z equal minus 1.25 and z equal 1 is 0.735 square units. You see how this works? It's almost like playing a game. You've got to figure out how to handle those areas in different situations. How about this one? We want to find the area to the nearest thousandths between z equal 1.24 and z equal 1.81. If you sketch it out, you'll see that it's the area that doesn't touch z equals 0. This is the first one that didn't either include or touch z equals 0. So you're looking for that area there. Well, how would you do that? Think about it. What is the area associated with z equal 1.81? If you were to look at it in the table, you'd get 0.465. What does that represent? That represents the area from 1.81 back to 0. Well, that's more than the area you want. You've got too much. You need to take some away. Well, how much do you need to take away? Well, you need to take away the part that goes from 0 to 1.24. So, the light bulb should come on. All I have to do is take that 0.465 and put it aside and go back to the table and look up 1.24, and that gives me 0.393. That gives me the area that I want to get rid of. If I take the 0.465 area and subtract off the 0.393 area, I'm left with the area that I want, which it turns out to be 0.072. So there's a little trick. Whenever the area doesn't include or touch z equals 0, you have to take the largest z value, look up the area, the smaller z value, look up the area, and then subtract the two. So the area under the standard normal curve between z equal 1.24 and z equal 1.81 is about 0.072 square units. Do another one. This time we're looking for the area between z equal negative 2.24 and negative 1.61. So this time both borders are to the left of 0. So we're looking for that area between. But because of symmetry, the area over to the left can be thought of as being the same as the area to the right. So instead of looking for the area between negative 2.24 and negative 1.61, just look for the area between 1.61 and 2.24. And the areas will be the same. And you can see by the symmetry that that's got to be true. And we just talked about how to do that. You take the larger z value, look up the area, take the smaller z value, look up the area, and then subtract. So the larger is 2.24. Look it up in the table, and you'll get about 0.487. That's the area from 2.24 all the way back to 0. Then look up the smaller z value, 1.61. That turns out to be 0.446. That's the area you want to get rid of. So if you take that away from the larger area, you'll end up with an area of 0.041. So the area under the standard normal curve between z equal negative 2.24 and z equal negative 1.61 is about 0.041 square units. You sort of see the game you're playing now. It's almost like playing a game. And to wrap it up, let me just summarize what I've talked about and sort of emphasize how it works. The simplest case is when one of the values happens to be z equals 0. Either 0 going to the right, or you've got a negative z, which means you're coming from the left towards 0. But in one case or the other, one of the boundaries is z equals 0. That's the simplest case. And in that case, whether the z value is positive or whether the z value is negative, you simply ignore the sign, look up the positive value of z, and that will be the answer. Second case, what if both values are positive or both are negative? That would be the case. The first one is where both z values are positive. The second one is both are negative. And we talked about that. All you have to do is take the positive values, whether they're negative or not, just take the positive values, look up the bigger positive number, the smaller positive number, and subtract. The larger minus smaller, and the difference is the area you're looking for. Third case. one value is positive and one is negative. Whenever one value is negative, one's positive, that means z equals 0 is inside. And when that happens, you break the graph into two pieces. You treat each piece as a separate problem and add the results. And we did one of those, at least one of those. And the last case is the area where you're doing the tails. Either z is bigger than some number or z is smaller than some number, where the value of a would be positive in the first case or negative in the second case. For example, either tail. The first one has the right tail where you have z greater than some positive value, or the left tail where z is smaller than some negative value. The procedure there, that's where the 0.5 came in. Remember the symmetry? You can look up the z value, ignoring the sign, and subtract it from 0.5. If you understand that, it's going to make your work in section 13.4 so much easier. So you might want to go back through this again and make sure you understand every bit of it. It's very important, and it'll make your life a lot easier in section 13.4.